So welcome everyone to this first lecture on continuum mechanics. So the course number is APL 701 continuum mechanics. So today is of course the introductory class. And I can see that there are students from applied mechanics, mechanical engineering, civil engineering, chemical engineering. So it's really great to have all of you here. There are PhD students, master students, MS students. So let me talk about the book, for example, the reference book. So there are so many books on continuum mechanics. Okay, there are lots of books, and there are several good books. And I thought that I will use a book which is freely available on internet, and it's also a very good book. So it's Continuum Mechanics by Rohan Aberatne. Okay, he's a professor at MIT. He's a very good professor. And let me share with you the link to this book. So can you see this site? I hope you can see it.
Yes, sir.
I'm going to share the link, the web link on the chat window here. All right, I hope you can see the chat, the link, and you can also open it now if you want. So here you have, this volume 1, which is a brief review of some mathematical preliminaries. So we are not going to look at this volume, which is actually essential to understand continuum mechanics. But you guys are also taking the course from Professor Arya Samanta, right? On engineering mathematics and computation. So he is going to
Yes, sir.
cover tensor calculus, tensors, transformation of tensors. So those things will be useful here. Summation convention. And students who are not taking that course, for them, I have my own lecture notes also. So I think last year I taught this course. Let me also share with you link to this course. It's not a course on continuum mechanics, by the way. So I taught this course on advanced theory of elasticity. Here's the link. Okay, so in that, when you open this link, you will find there are lectures, and up to lecture 6, I talk about the mathematics required to understand the course. So you can, there are hand notes. You can click on the hand notes, and you can find the material. Okay. And of course, if you don't follow the hand notes, which I won't doubt, because I don't write everything. So in that case, you simply click the video link also. So those of you who are not taking the course from Professor Arya Samanta, please go through the first 6 notes. That will really help me so that I can cover many more things. Okay, so as I told you, volume 2, you see here, that's the continuum mechanics. Okay. And we will try to cover as much as possible from this book. Yeah, so this is the contents page. So chapter 1, see, he will also be having different notation, and the notation that I will be using will be slightly different. I mean, it will be quite different. So, but the concepts are all from this book. Okay. So chapter 1, chapter 2 is on kinematics. Then chapter 3, chapter 4, chapter 5, chapter 6. So these are all relevant topics. Chapter 7, chapter 8. So we'll see how much we can do. And I'll try to keep all of you together. You know, we'll go all along. So I'll try to be slow. So this is volume 2. Okay. From that link, you have to click volume 2. And for the mathematics part, please understand the concepts from Professor Arya's course. Okay. And else you go through my webpage for course AML 841, lectures 1 to 6. Okay, is that good for everyone? So that's about the reference, and like I told you, the notations will be different from the reference book. Notations used in the class will be different from the reference book. But the same concepts, right? But the same concepts will be taught. Okay, then comes the grading policy. Many of you must be worried about this. So in this online semesters, we have one midterm and one final exam or major exam. Right? Well, this is point number 2. This is 1, and major exam is also 1. So midterm will have 30% weightage, okay? Major exam will have 50% weightage. And then I will be giving you quiz throughout the class. And I don't know how many, maybe 2 or 4. And they will really be quiz type. So, and it will be automatically graded, okay?
Yes.
So that means you just have to take the correct option. You know, so these two courses are taught separately in UG, but continuum mechanics is a way to teach the two courses in one single framework. Okay? So you might think it's so interesting, isn't it? So continuum mechanics is a way to teach or learn both the courses in a single framework. See, as the name suggests, it's the mechanics of continuum. Okay, so this continuum is the keyword here. And what does it mean? So, of course, literally it means continuous, right? Continuum, something which is continuous. There is no gap. It's all continuing. And continuum, if you go to dictionary, it actually means a body like I said, it is continuous. Having no internal gap or void. Okay. But do you know of any body which is like this? Can you name any body which is continuous, having no internal gap or void?
So at the macro scale, we can say this.
Right. So you have raised a very important keyword, that is at macro scale. So basically, no body is a continuum. Whether it is your laptop or your human body itself, or your walls, any machine, metal. So to your naked eye, of course, it looks like it's all continuous. But when you put a microscope, electron microscope, and zoom it at a local region, you start seeing the microstructure. You start seeing the atoms, and you of course also know that any material is made up of atoms. And there are, for example, crystal structure at the nanoscale, and between two atoms there is a gap, right? So at that scale, it's all atoms, and it's a discrete material at nanoscale. So I should say that there is no body which is actually continuous. They are discrete at nanoscale. But for practical purposes, as you know that when we see it from the naked eyes, the things which are around us, they all look like it's a continuous body. And there's no random fluctuation that we observe. So at nanoscale, they're all vibrating, there's a random motion. But at the continuum scale, so we say it's at the continuum scale, or the scale at which we are seeing something. So at that scale, those fluctuations of nanoscale are gone. The discreteness also, we don't see it, right? So that's where we can treat materials as continuum. Okay. So at macro scale, materials can be treated as continuum. Okay, and so this course or continuum mechanics is the mechanics of bodies at this macro scale or continuum scale. Okay, So we can say this continuum mechanics is mechanics of bodies at macro slash continuum scale. Okay. See, I just talked about the nanoscale atoms, but a material. Some of you who would have taken material science course, you would know that at micro scale, for example, there are grain boundaries in material. So again, things look so smooth at the naked eye scale, but at micro scale, you start seeing grain boundaries. Grains having, so suppose this is your body, then at micro scale, you have the grains. And inside grain, you have those lattice structure, which are oriented differently in different grains. Right? So again, there are those things, but at macro scale, those things are not visible. And the material can be treated as being uniform. There is no grain, it's all uniform. Okay? So that's why we say it's the mechanics of bodies at the macro or continuum scale. But of course, these structures at nano and micro scale, it affects the behavior of the body at macro scale. It should somehow affect. But it affects in a different way, okay? So we'll learn about those things as we proceed. So it helps in the sense when we say it's at macro scale, then you don't have to model those grains or the atoms individually. You can model a material or a body as being a uniform body, continuum body having no gaps. So you can forget about individual atoms, individual grains, and treat it as a continuum body. Okay, so it helps as far as the kinematics is concerned, which you will see as we move along. Is that okay to everyone?
Yes, sir.
Yes, sir.
Yes.
All right. So now you see that in the scheme that we have talked about till now, you can have both solid bodies as well as fluid bodies. Both are continuum, right? You look at water, for example, water is flowing. It's continuum, continuous body. Similarly, a solid body also is continuous body. Therefore, both can be treated or both can be investigated within this continuum mechanics framework. Solid, liquid, gas, all of them. Okay. Now the first thing, whenever we do a theory, the first thing that we have to ask is how are we going to represent a body? So it's a continuum mechanics, mechanics of continuum. So how are we going to represent a continuum so that we can address them? How to represent, which could be also mathematically. Okay, so you see, this is your arbitrary body. It can have any shape. So how do we mathematically describe this body? That's the question here. Now we have to describe, we have to understand what are the different features that we want to describe. So I already told you we have to look at it at continuum scale. We don't have to look at it at micro scale or nano scale. So that means we are not bothered about representing individual atoms or the individual grain boundaries. Okay? We are just bothered about modeling it as a continuum, having no voids. So you can, isn't it that we can think of it as collection of particles, and somewhere they also say material particles, and there's an underlying assumption that which are collection of particles which are present in a continuous fashion. Okay, so you can think any point you pick, there will be a material particle. Any point in this body, when you pick, you start, there will be a unique material particle at that point. Okay, and this body is just the collection of those particles. And you understand that a body is actually um, it's a three-dimensional body, right? It stays, or it is there in this three-dimensional space. So how can we represent those particles mathematically? Any idea? Can anyone tell me how to represent these particles mathematically?
So by locating their coordinates, or by locating its center of mass, coordinates of center of mass.
Each of the particles individually. And these particles understand that they are not the atoms. It's not the atomistic viewpoint, it's a continuum viewpoint. Okay, so it is very critical to know that the particles are not atoms, because we are looking at the material from the continuum viewpoint.
Sir, by using summation notation.
By using summation notation, correct, by using the position vector, right? So there will be a unique position vector associated with each of the particles, and that position vector will mathematically represent a particle, right? So suppose there is a point which could be origin. Okay, let us denote that by O. So with respect to that point, each particle will have some position, right? And say this particle here is the particle P. And the position vector of that particle, let us denote it by X. Okay, and this has to be a vector, right? Because it's a position in three-dimensional space, so it will have three components. See, it is also very important for you to understand what is vector and what's the difference between a vector and the three components of a vector. It is very important for you to understand. And then once you know vector, what's a tensor? So please go through my notes, okay? And I'll try to do some of them here, of course. Also, so it is fine that a particle you can denote by its position vector, isn't it? But you know that the body is evolving in time, right? The body is evolving in time. So if it is at t equal to 0 over here, at some other time, it could be at a different location, right? And it will have a different shape also. So the same particle which was over here, it could have moved and come here, right? So that particle would have followed this pink trajectory. So that's the trajectory of that particle P. So now it has a different position vector, isn't it? So if you think of it now, so it has a different position vector. Let us say y. So when we say we can represent a particle using the position vector, then you instantly also notice that the position vectors are not fixed for a particle. It is changing from time to time, right? The position vectors are changing from time to time. The position vector of a particle is changing from time to time. If any one of you are not able to follow anything, please interrupt me. So then that will bring some ambiguity, isn't it? We initially thought that through position vector will denote a particle, but also understand that at a position vector, let us say this position vector, you can have different particles at different time at this position vector, right? Suppose this position vector is z. Then maybe at t equal to t1 you have one particle here, and at t equal to t2 you have a different particle, right? Because the body is flowing, so at this position vector you will have different particles passing through. So that brings some ambiguity, that so that means just by position vector we can't specify a particle uniquely, right? Because the same position vector can be occupied by different particles at different time. So what do we do then? How do we then uniquely specify a particle? Anybody, can you think of? What we are trying to figure out, is there a one-to-one relationship between the particles of a body and a mathematical number? Because when we want to do mathematics of the body, right? Because our goal would be, for example, to simulate the body as it is deforming, finding, for example, stress in the body. So for that, we need to have some mathematical equation, right? So we want to simulate a body, and we want to track each of the particles because this is the mechanics of continuum, and we want to see where each of the particles are going. Only then we can then form our body, This is a function now. Which has so many numbers. At different time it has different output. This function of position vector of a particle has different output as at different time. And when you are studying a body, you are studying it for a given range of time. And it would be nice if you have one single number which holds for every time for a given particle. Isn't it? So it would be nice if we have one unique number associated with every particle, which holds for all time that we are interested in. Okay, so what's the remedy then? Well, somebody has already written that we do it by taking reference configuration. So you have the body which is flowing in time or evolving in time. So this is t equal to, let us say, 0, t equal to t1, this is t equal to t2. And there is a material particle here which may have come over here and then it may have gone over there. And this particle may be following this green trajectory in space. So you can see that the position vector of this red particle is changing with time. So how do we then, can we think of a unique number for this red particle? Okay, you already have a class at 9. So yeah, so I'm going to stop here and we'll continue from here in the next class.